So, as I mentioned to you, we need to introduce some now empirical corrections to the criteria that we just developed here in order to take into account some specificities of our situation. In particular, in the presence of waves, we are used to subdivide the shear stress into components. The shear stress exerted by waves. It's a component that is given to currents and a component that is given to waves. So we indicate tau as tau b, which is given by two components. Tau b because to identify the specific situation of waves, and the two components of current and waves. There are empirical relationships for computing them. As I told you, I mentioned to you before, once that we know the behavior of waves, we can compute tau, we can compute the shear stress. The empirical relationships are given here, in particular by these two, where you have a parameter that is computed through another empirical relationship. You don't need to remember this. It's just fine if you remember that it's usual practice to subdivide the shear stress into components, waves and currents. Okay, and then also there is a friction factor, again, empirical relationship for computing it. In the web pages I wanted to give you all the elements, but for the exam you don't need, of course, to remember all the empirical formulations. Keep in mind, as a general premise that I should probably have given to you before, everything is in this web page, including the Hudson formula, is presented in a document that is freely accessible on the web, which is linked at the top of the page. And the document, the link is here. If you just click there, you get the document. It's a document that is quite long, about 100 pages. I made a synthesis of what's relevant to you, and it's compiled by Van Rijn, who is an authority in coastal engineering. And here you can find all the details and also Hudson formula, etc. And if you go down, there is everything related to, there is much more with respect to what I did. I think there are also the sketch of sheets and etc. Let me just get to the point where, or let me search for sheets maybe. Okay, sheets curve. Here it is, critical shear stress method. And here you see the sheets diagram, and here the scheme from which I just took, in particular this one, slope. Okay, and that's it. I just wanted to give you this information. And now, sorry, I closed the window. I shouldn't have done this. Just 1 second. Okay, now let's see and other issues that we have to consider. The effect of slope, and in particular here there are some corrections that are introduced because in order to take slope into account. Why these corrections are introduced? Because I just wanted, okay, this relationship here, which is simplified with respect to mine, is a relationship that applies only for beta equal to 0. If beta is different from 0, the relationship is mine, which means that you have to correct the sheets diagram, okay? And sorry, I forgot to tell you this before. So the sheets diagram applies only in this case here, where beta is equal to 0. Instead, if you want to apply my relationship, the sheets parameter needs to be corrected. And let's see how it's corrected with formulations that you don't need to remember. So you just have to correct the shear stress with two coefficients, and two coefficients that take into account the slope in the two directions, because the side of the groin could be sloped in two directions, in the direction of waves of the heating force, but it could be also sloped in the other direction. And therefore, depending on the two angles of slope, you need to introduce two correcting coefficients. Again, you have all the formulas here, but you don't need to learn them. And then there is the effect of hiding. Just a couple of lines, please.
Sorry, that diagram, so that diagram is related just with beta equal to 0.
Yes. So you have to use a different value of the Schiltz coefficient, basically, for taking into account the slope, or you correct the value of the shear stress.
So the value of the constants, 0.05, is equal to the C times tangent of phi.
Yes. Okay. And phi is the friction angle of the material. Okay, and then you have the effect of hiding and the effect of armor unit's shape that is described here on just a few lines. If you want a complete description, refer to the document that I showed you, but you don't need it. At this level of your education, at this stage of your education, you don't need to go into these details. I just wanted to introduce, as I said, the Schiltz formula because I think it is instructive, because it shows you that indeed there is some physics behind it. And then the Hudson formula, you already know it, so I just reported it here, because in my opinion it should follow the Hudson formula, the example of the Schiltz formula, because it's purely empirical. Hudson is purely empirical, while Schiltz has a physical basis. And that's it. Okay, so let me just make a summary. We approached with a very empirical approach the design of groins. First of all, we studied in the previous lecture what is how to design groin spacing and length according to the 1/3 rule. And therefore we learned how the profile of the beach is modified by the presence of groins. And then we took into account, also we discussed permeability and bypassing. And then we studied here the stability of the armor units that gives to you a means to verify whether the slope for the sites that you adopted, like if you decided to adopt 1-1, you may have doubt that it's not stable. And these relationships give to you the means for studying the stability of the armor units. There is still, even here, a very consistent empirical part, which is related to the fact that the action of waves is not easy to represent physically, of course, and therefore you have some uncertainty, which means randomness. The same procedures, you are already more or less the same procedures you have studied for breakwaters. I'm not talking in my lectures about breakwaters. I will display, when starting from the next lecture, also some lecture by me on breakwater design, which is a bit complementary with respect to what Professor Archetti usually does, and you don't need to learn it. I'm not asking anything at the exam related to breakwaters. And I will just show to you the lecture, because I think that some information may be complementary, and therefore I think it may be useful for you, especially in the future, to have also my reference related to the design of breakwaters. It's still not there, that lecture, but you will find a link with designing breakwaters. I just wanted to inform you, and I think I need to make it explicit in some way, that this year in the exam I will not ask anything about it. While the next lecture that we have to deal with, it's more relaxing, it's nature-based solutions. It's more relaxing because there is no analytics here, and this is very descriptive. It is a usual situation when we talk about nature-based solutions. Very often we end up with a design that is qualitative rather than quantitative, and then the treatment becomes more descriptive. What is the reason why nature-based solutions very often need a qualitative design? There is a very good reason, and the very good reason is that nature-based solutions, as the name suggests, are based on the use of natural solutions. Meaning, natural means something that is live, something that is strictly related to ecosystem. So we use ecosystems to protect what we want to protect, in this case, a beach. We use something that is living, something that is related to ecosystems. And therefore, you understand that predicting the behavior of something that is living, something that has to grow up and has some properties that depends on the strength of a living organism, you understand, if not living, something that is in any way subjected to natural evolution, you understand that it's something that is very difficult to predict. On the other hand, nature-based solutions have the advantage of being based on soft solutions, soft methods. What does it mean, soft? Low structures, something that can be adapted. And this is the very good, one of the very good behavior, very distinctive behavior, distinguishing behavior of nature-based solutions. The fact that they can be adapted. You can refine them during their life, and you can also recover them in a quite easy way, like the way we follow when they were created. Of course, another good thing of nature-based solutions is that they are natural, so they are part of the environment, because in order to be functional, in order to be effective, they have to be a part of the environment, something that is not impacting, less impacting in terms of visual, in terms of tourism, in terms of also sustainability. Because, of course, if something is natural, it's by definition sustainable with the environment. So this is the reason why they are so popular, because they are part of the environment, are natural and sustainable. On the other hand, they have also the good technical feature of being flexible and being adaptable. What is the problem of nature-based solutions? The problem is that their efficiency, their functioning is subjected to uncertainty. And this is why the design is qualitative. Sometimes you have to try. It's a trial and error procedure. This is indeed quite a problem. And there is another problem, which is the time required for their development. They are not something that can be immediately put into practice. If you build a seawall, you understand that in a week you can build it and it's effective. If you build a groin, it's very effective because it's something that you can build very quickly. Other kind of interventions that are based on the use of ecosystems require a longer time, and therefore, you know, the effectiveness is sometimes questioned by the public. As for any classification, once again, don't assume that there is a clear difference between structural interventions and nature-based solutions. For instance, if I talk about a groin, one would say that it's nature-based because it's natural material. And also, it's based on the development of an ecosystem, because inside the groin you have, anyway, life that grows up and therefore protect the natural ecosystem of the beach. And the groin is something that could be easily classified as a nature-based solution. Usually we classify it as an intervention, as a structure, because it's something that, you know, it's not really natural. We want a nature-based solution to be natural. A groin is not natural. But on the other hand, if you use natural material, you know, one could say that it's nature-based. Another possible solution, which is classified as nature-based, it's the first that we will take into account. It's protection of beach with cobbles. Cobbles are like loose grain and loose gravel. The gravel is less susceptible to erosion with respect to sand, and it's typically considered a nature-based solution. But you understand that the difference between a groin and a cobble berm is the technical term to identify when we put gravel over the sand in order to protect it. You see that the difference, one could say that they are the same type of intervention. So don't assume that the classification is strict. Okay, so let's see this nature-based solution. Remember that I don't think it exists a unique solution. So if, as an engineer, you take an attitude like, I like nature-based solution, they are the way forward, and the only way forward, you are for sure wrong. On the other hand, if you neglect the usefulness of nature-based solution, you are again for sure wrong. I mean, the good thing is to know what are pros and cons of each solution, and depending on your case, you go there, and based on your creativity, you find either the right combination, because you could combine structural and nature-based solution, or based on your creativity, you try what is the best solution, you identify what is the best solution for that place, without a unique recipe. You have to be flexible, because otherwise it's like people who say, I don't want reservoirs, I don't want artificial reservoirs, I don't want dams. It's a stupid attitude, because without dams we wouldn't have developed our society like we did in the past century, and in some cases they are still needed. You need to build a dam if you want to resolve particular situations. On the other hand, there are some engineers that say the only solution is given by dams. It's a stupid attitude, because in some cases you can avoid it. And if you can avoid it, for sure, it's good to avoid it. Any structural intervention, when we can avoid it, for sure it's to be avoided. But you have to carefully evaluate, and also you have to take into account the cost, of course, because sometimes structural solution will be more costly with respect to nature-based one, and sometimes it's the opposite. Okay, so let's take into account some solution. First of all, when we talk about nature-based solution, there is a flourishing literature, and some people try to classify it. This is a public domain graph. I think it's interesting, and highlights that we may identify three types of solutions. The difference is very simple. Type 1 is you make a better use of what's already there in terms of ecosystem. This classification is based on ecosystem. You have to intend ecosystem in the widest sense, in the sense of any natural system. So a groin may be an ecosystem, because you have life anyway there, and it's part of nature. So it may be an ecosystem. A cobble berm is for sure an ecosystem, because if you don't protect your beach and your beach is taken away, you have an ecosystem there that is taken away. If you put a cobble berm, by definition, it wouldn't be an ecosystem in itself, because it's just gravel, but beneath it, in the sand that you are protecting, there is an ecosystem. So let's define ecosystem in the widest sense. As I said, anything that is natural, because if it's natural, it hosts some life. Even in a desert, you have an ecosystem. Okay, so type 1 is the soft one, better use of natural protected ecosystem. And you see that in terms of number of stakeholders, you go down. In type 1, the number of people that can benefit from it is reduced with respect to the other type, where you add something to existing ecosystems. And here you have the maximization of the delivery of these services, of course, you maximize the delivery if you evolve, in the sense that you are evolving ecosystems, not just using those who are there. Type 2, it's sustainability and multifunctionality of managed, still existing ecosystems, meaning that you try to get what's existing, you manage it in order to get additional functionality. For instance, let's think about vegetation. You could use that vegetation to cleaning, to sanitize water. You know that there are some techniques that you use in order to sanitize water, vegetation. It's called the phytotechniques, phytoplants, etc. So this is an existing ecosystem where you add a functionality. Type 3, you create new ecosystems. Like you put vegetation over the berm where vegetation is not there. It may be that it might have been there years ago, now the berm is not protected, the dune, let's say vegetation is typical of the dune. You put vegetation over there. This is a very simple classification. Greening cities. This is a very popular solution today. It's not just related to coastal engineering, but you may have heard that there is a movement, a technical movement that is trying to make cities more sustainable by greening them. And greening means that you put vegetation, but also you use that vegetation for cleaning water from, drainage water from the street, for instance. So in some solutions, the drainage water from the street is not delivered to the sewer system, but it's delivered to zones, green zones, where vegetation has cleaning capabilities. And so there is a better management of existing ecosystems and new ecosystems like green roofs, for instance. This figure is just to remind you that on nature-based solution there is a flourishing literature. I tell you that for engineers it's a challenge because there is a lot of literature describing what solutions you can use. When it comes to the point of design, you don't find anything. And this is, or not anything, but you find little information. For the very reason that I mentioned to you, it's not easy to predict how this system works. And therefore there is little information on the design. And the same for nature engineering in general. So when you go, for instance, in the field of fluvial hydraulics, there are many nature-based solutions that are proposed by the literature, but the question is how can I design it? Because with the concrete it's easy. You know the properties. Do you know the properties of a living tree, of a living element? Unfortunately, still we don't know much. So I want just to clarify to you that when it comes to nature-based solution, it becomes a challenge for an engineer. I tried some years ago to develop some thesis, master thesis with some students, like, let's inspect a nature-based solution, so try please to make a thesis on that. And the students had problems, because they said there is so much on the web, but I don't find anything technical. Or if you find something technical, it is very specific. It's something that is difficult to generalize. So it's a topic that is a bit challenging, and it's also interdisciplinary, because you have to deal with ecology, and you have to work with ecologists, you have to work with people that know how to manage living organisms, but on the other hand, they don't know how the properties, the technical properties of these organisms. They can tell you what is the chance of survival, but if you ask what is the resistance of this material to several stresses, it's difficult for them to quantify them to you. So it's always challenging. So you will see my description very descriptive, with no technical indication. The good thing, as I said, is that you can try. Okay? So let's start with, for any solution, there is then a description of strengths and weaknesses. This is my attempt to be technical. So I cannot give numbers, but a first step is to identify what are the strengths and the weaknesses, so you can get a technical idea. Okay? So, cobble berms. As I said, it's gravel put over the beach, and it can be also named dynamic revetments. The term is written here. Dynamic revetments. They are synonyms. Why dynamic? Because they can move. When you talk about beach revetments, it means that you are putting in place something like boulders to protect the sand, and the revetments are often meant to be fixed. Dynamic revetments, they can move. And what you do is to work on the berm. Remind the difference between the berm and the dune. The berm is formed at the end of wave run-up. It's usually formed during, it is developing during the good season, the good weather season. It's typically eroded during storms. In the berm you don't have vegetation. The berm, you have sediments transported by the waves, so it's something that elevates a little bit over the beach. Behind the berm you can have the runnel, which is like a small channel with some salt water. And as I said, the berm is the end of the wave run-up, typically during the high season, meaning the summer season, okay, the season with good weather. Beyond the berm and beyond the runnel, you have the dune. The dune is much more elevated, and typically it is placed where the big storms, the wave originated by big storms, can extend. It's the max length reached by the max elevation into land, the max extension into land that is reached by big waves. And therefore you have the position of sand during high storms. During high storms you have a lot of sediment transport, and this is why the dune is so elevated. And the dune may be formed by the sand that is taken by the berm. While the berm is something seasonal, the dune is more permanent, and being elevated can host vegetation. As we said, it's vegetation that is resistant to spray, to salted spray, but there is some vegetation because there is fresh water, because it's elevated. So there is storage of water during rainfall, and so the plants can survive. We are talking here about the berm, protection of the berm. The berm is to be protected especially during the winter, so it could be also a seasonal solution. You may just put cobbles there during winter, and if cobbles during summer are impacting tourism, you could remove them. It is easy to remove them because you can just use a sieve, or you can just scrape scrape means, you know, I'm not sure whether you know the term, okay? Scrape the superficial layer and remove them during summer. And so, the good thing of the cobble berms is that cobbles are similar to a natural environment, and therefore, you know, they may be a bit tedious for tourists because they like more the sand, but still they are not so impacting. In fact, in some cases, you may notice that you go on the beach and suddenly you find some cobbles into the sand. Somebody can, in my case, I wonder, it's strange because there are cobbles and there are no cobbles in the dune, and there are cobbles here in the berm, and the reason is that probably somebody put them there for reinforcing the berm. You know, the berm is an important protection because, you know, the last protection is the dune of a beach, but the dune is the end of the beach. The berm is a part of the beach that is more elevated and protects the part of beach that is behind the berm and the dune, which is the part of beach that we use more. Because the berm is located where water every day gets to. And so when we want to take our sunbaths, we don't go typically over the berm because it's wet. We stay in the part of beach that is between the berm and the dune. So, you see what's written here, and this intervention should be designed to look as close as possible to the natural environment, and should favor the development of a spontaneous ecosystem. And this happens if you ensure stability. So if the cobbles are not frequently displaced, then you may have an ecosystem that is flourishing there. Ecosystem in terms of micro-invertebrates or other animals that live buried into the sand. You know, it's widely used, and let's now see what are the strengths and the weaknesses. Let me say, it's indicated here, the design of cobble berms is mainly based on empirical relationships that were derived through lab experiment and the study of natural beaches. And it's something similar to the sheets experience. And here there is a link where you can find no, it's a link to one of my web pages. Let me see where the links points out. Just 1 second. It's a bit slow. Okay, let's go there later. But as I said, from a technical point of view, it's not really, yeah, it's the previous lecture. Yeah, because you could start the stability of the berm with similar relationships. Now, strengths and weaknesses. First, the strengths. Placement and construction are simple and less expensive than traditional infrastructure, for sure. You bring just cobble there. They appear as a natural environment, less expensive, it's already written here, so this is to be corrected because this is repeated. They are flexible under the attack of waves and therefore do not fail as a seawall can, because a seawall may fail. You know, the cobble berms, they don't fail, they are very flexible. The worst that can happen is that they are not efficient and therefore you have erosion, but you have not a sudden failure. And also, they are not an obstacle to the use of the beach by tourists. And they may become buried by sand during summer. Why is that? Because during summer you have displacement over the berm of sand. Because we have seen that typically we have accretion during summer of beaches and erosion during winter. So during summer, the cobble may disappear. In fact, this is the situation that you find in some beaches, as I mentioned to you. If you dig into the sand, you find some cobbles, which may seem strange because clearly it's not really natural. Now, weaknesses, they provide less protection than a revetment or a seawall, for sure. They require frequent maintenance because the material can be eroded and can move. On the other hand, this is also a distinguishing feature because they can be renewed quite easily. Cobbles may be thrown landward during a storm. This is something that we often don't consider, but indeed it's something that may happen. Sometimes when you have very violent storms, you get cobbles that are thrown by the waves landward, and they can cause some significant damage. And, you know, from the point of view of the recreational opportunities, it's a bit of a problem. Artificial dunes, sandbanks to recreate a dune or to create a dune. We know why a dune is important. It's the last protection. And therefore we can use, as I said, sandbags or geotextiles. You know what are geotextiles, correct? They are a kind of carpets that are displaced over the soil. It may be a beach or sometimes they are displaced over hill slopes. And they have particular properties of resistance to tearing, to erosion, and therefore by displacing these geotextiles over the soil, you protect the soil from erosion. And so artificial dunes are very widely used, And of course, you have to design several features. The most important probably is the height of the dune crest. So how high should it be? Of course, we have to look around, we have to try to mimic the natural environment. If it is too high, of course, it's not going to be very functional because it may be unstable. But when a geomorphic feature, meaning when a form of land is non-natural, it means that it's not in equilibrium, because natural forms arise from equilibrium between contrasting forces. So if you make an artificial dune too high, it means that it's not natural. It means that it's not stable as a natural form. This is something to keep into account, because one could say, okay, given that I have to make an artificial dune, I make it very high. But if you make it very high, it means that it's probably going to become unstable. Because, you know, these geotextiles, once that have been displaced, once that the sandbag have been displaced, they are subjected to degradation. And the container is going to disappear, the geotextile is going to disappear in the long term. And therefore, what remains is the sand that is below it, or the sand that is inside the bags. So if it is too high, it's unstable, it's going to be eroded. And therefore, we have to try to understand what is a natural shape. And the best way of doing that is looking around. Looking around or other places with similar behaviors. This is the best. It's a way to make a real-world lab experiment. I mean, it's extremely useful when you can refer to natural shapes in their natural scale. It is the best lab experiment that you can make. Lab experiments may help. There are some people who study, I'm not sure whether I think I have a video that I could show you. They